Welcome to Techno Sapiens.
Hey everyone, and welcome back to The Explainer. Today, we're diving into something that is literally happening right behind your walls, out on the streets, and across the entire power grid, right this very second. We're tackling this everyday mystery of why electricity, well, loses its punch. You see, the power that fuels our entire lives goes on this massive, hidden journey. And what happens along the way? Well, it's a pretty fascinating story of physics and engineering. Ever wonder why electricity gets weaker over long distances? Think about it. We plug our devices in and just expect instant, perfect power, right? But the reality is actually a bit different. The electricity arriving at your outlet or, powering some massive factory isn't actually as strong as when it first left the power plant. Something out there is actively sapping its strength. And it's this crazy phenomenon that dictates exactly how our entire world is wired. All right, so section 1, the weak power mystery. Okay, let's dive into this. We've got a victim here, our electricity. And we really need to understand exactly what is draining its energy. So to solve this mystery, we have to look at its environment. Electricity doesn't just magically appear out of thin air, right? It starts its life at a power generation plant with a very specific set voltage. Think of this initial voltage as its starting energy level. But it can't just stay at the plant. It's got to travel. Sometimes just a few miles, but often we're talking about traveling vast distances through a super complex network of cables just to reach your home, or a local business, or maybe a heavy-duty manufacturing factory. It is a grueling commute. And as it travels through these cables, it isn't moving through some empty void. It physically has to push its way through the actual material of the cable itself. Which brings us to section 2, resistance, the hidden culprit. Now, what's really interesting about this is that as electricity makes this epic trek, it encounters an invisible force that fights it every single step of the way. This unseen villain doesn't sleep, it doesn't stop, and, wild enough, it's built right into the very wires that are supposed to be helping the electricity travel. We call it resistance. Basically, it's an inherent property of the cable itself. So as the electrical current flows, as all those little electrons try to move from point A to point B, the physical material of the cable actively resists their movement. The electrons are constantly bumping and pushing against the cable's internal structure. It is literally a microscopic battle happening right inside the wire, with the cable fighting back against the flow of electricity. And honestly, this is where distance becomes a huge problem. It sets off this inevitable chain reaction. Step 1, you have a longer cable length. Makes sense, right? The further the electricity has to travel, the more of that physical cable material it has to fight through. So, step 2, this directly leads to increased cable resistance. You are basically just extending the battlefield. And finally, step 3, because of this extended resistance, way more voltage is lost along the way. So, distance actually acts as a multiplier for our culprit. The longer the cable, the more the resistance, and the weaker the voltage becomes by the time it reaches the end of the line. In the biz, we call this the voltage drop. Okay, moving on to section 3, the water pipe analogy. Now, if visualizing electrons fighting through a wire feels a little bit abstract, don't worry. Let's think about something way more tangible. And this brilliantly illustrates the concept. Imagine you are pushing water through a really, really long pipe. The further that water has to travel down the pipe, the more energy it loses simply because of the friction of rubbing against the pipe's walls. By the time it reaches the very end, the water pressure is just much lower. Well, electricity experiences the exact same thing inside a cable. The flowing electrons are the water, the table is the pipe, and the electrical resistance, that's the friction. Just as the long pipe saps the water's pressure, the long cable saps the electricity's voltage. It's a perfect match. Let's jump into section 4, engineering a solution. So human ingenuity doesn't just accept defeat, right? We can't simply let all our electricity drain away before it powers our modern world. Once we identified the culprit, resistance, and understood exactly how it drains our voltage over long distances, engineers stepped up to defeat this physical limitation. To make sure you actually get the power you need, engineers developed a very specific toolkit to beat the voltage drop. First off, they can use higher voltages right from the start. Think of this like pumping the water with incredibly high pressure right at the source. So even after it inevitably loses some energy along the way, there's still plenty left when it arrives. Second, they install thicker cables. Going back to our analogy, a thicker cable is just like using a much wider water pipe. It gives the flow way more room to move, which dramatically reduces the friction or, the electrical resistance. And finally, they utilize larger conductors overall. By widening the path, they make it drastically easier for those electrons to flow, successfully neutralizing the nasty effects of a long-distance commute. So the crucial point is this. It all boils down to an ultimate unavoidable formula. Check this out. Whenever you have a long cable,
combined with the inherent physical resistance of that cable, and you push an electrical current through it, the guaranteed result is a voltage drop. It's just an unavoidable fact of physics. Electricity simply cannot travel a long distance without paying a toll to resistance. But by fully understanding this formula, we've learned exactly how to manipulate the variables, like upgrading the cables and boosting the initial power, to keep our entire grid running smoothly.
Well, we've definitely covered a lot of ground today, pulling back the curtain on the hidden journey of electricity, so I want to leave you with this final thought. Next time you sit down at your desk, plug your phone into the wall, or even just switch on a light, ask yourself how much energy was lost just fighting its way to your outlet. It is so easy to take instant power for granted, but behind every single charge is an epic, miles-long battle against resistance. Thank you so much for joining me for this explainer. Keep asking questions, and I'll catch you next time.